thanks for having me here. So I will say something about 6G for dependable communications, and this is work out of the Deterministic 6G project. And the outline is that I want to give some general reflections on 6G because there are a lot of activities ongoing in 6G, and we have to embed the work that we do in Deterministic 6G on this dependable time-critical communications, of course, in this context. And then, so what we see at large, and I think several of this is interest in this workshop today, is there are several architecture trends that we see will materialize in 6G, and this is that we will have an adoption of a data-driven architecture that is enabling for AI. We see that we continue the journey towards cloudification and virtualization and distributed compute as a platform on which services but also networks are realized. We see a trend towards flexible topologies, and edge computing is taking place, enabling the possibility to offload functionality from physical devices. Then we see a strong trend towards automation of networks to enable optimizations, and there the big trend is to go into intent-based automation. And there are new ways being explored on interacting from the network with the application domain, making the network more programmable via network exposure. And then, of course, the value that we bring in with 6G has to be shown with key value indicators and sustainability. And something that I want to highlight a bit at the beginning, that it's important in this trends that we are pursuing, that we consider on how we come into an efficient migration introduction of 6G. And what is important in that level, if we come into a structured layered form of this, of a 6G architecture, that we think of where is really the focus needs to be put into as we start preparing soon to bring this into standardization of saying where is it where the effort should be done. And this is then, of course, on identifying the points of interoperability that needs to be addressed, where different domains come to each other and need to interwork, or where we come into multi-vendor kind of scenarios, and interoperability is of key importance. And there are several of these interfaces which are of prime importance. One is, of course, the radio interface to connect any device to the network. But then we also need to think of other interfaces that are important, for example, for allowing the interaction with the applications via exposure, or having interfaces into an infrastructure side for using transport for connecting our networks, or making use of a cloud infrastructure or a data pipeline for an AI-enabled network. And I think it's always important, in particular, and the more we come into the systemization of 6G, to be aware of where these interaction points are. And if we look into how we have come to where we stand today, then we are coming, of course, from a number of generations. We've had our 3G to 4G migration, and now we are looking into 5G. But if we really look close into 5G, then we see that we still see two variants of 5G. There's the 5G non-standalone solutions, where we basically mainly introduce the 5G radio interface that connects to the 4G network. And we have the standalone, where quite a few of the new functionalities that were specified for 5G become available. And now we have to think of how do we make this step into 6G. And I think it's good to think a little bit on how we made this journey with 5G. Because as we migrate towards 6G, when we look back in how we did this in the migration from 4G to 5G, then there was a large number of connectivity options introduced on what kind of devices connect to what kind of network in what form. And this led to a quite large number of migrations options that were specified. And that was quite some standardization effort with all these different options, and it fragmented the market. When we look into the market numbers of today, then we see that we have roughly 1.6 billion 5G subscribers, and 20% of the networks in the world are currently using the standalone 5G architecture, and roughly 90% of the devices support 5G standalone. One way to look at this is that we put a lot of effort into standardizing 5G, and it has not hit the market. All the capabilities which come with standalone 5G are simply only on a fraction of the market available. And also a lot of the migrations options that we put a lot of effort into standardizations of getting them standardized have actually not appeared. And that, I think, is an important message for us as we start thinking of going towards 6G, that we really think, what is it that we should put in focus that creates value on the market that leads to an adoption? And there, I think it's very good to have a lot of open discussions here so that we have a common understanding as we as an industry are preparing for going towards 6G standardization soon. And what we see as a way forward for going into the 6G standardization, we would like to see that we come very quickly to a 6G standalone kind of solutions, which allows 6G devices to directly connect with the 6G radio access network to the core of the network with the corresponding functionality. Because that is basically leads that we get the full potential of what we put into the 6G standard, make it available to the market in the early phase. At the same time, we see that we are still very much in the market is very much in the adoptions of the 5G core deployment. And this will continue during the 2020s, which means from an economic feasibility, there will be a lot of friction if we to convince the market that there will be yet another core network that needs to be deployed in 6 to 8 years, which means that we see at the same time the 5G core has been built of being a rather flexible network platform that enables quite some service innovations. So we see that it is feasible to consider that the core functionality for 6G will be introduced in an evolutionary path based on the 5G core network platform. But then something which is very important is then, of course, that we make it possible for 6G radio access networks to be deployed. And that means an efficient way to do this, and I think we heard this in an earlier presentation as well, is to build on multi-radio spectrum sharing that allows common spectrum to be used for both 5G and 6G connectivity, and allows therefore an early and fast deployment of 6G radio network functionality. And in this context, that is the context in which we consider the work that we do in our Deterministic 6G project. So the Deterministic 6G project is a project that started last year and is running for 2.5 years. And we are working on providing deterministic and dependable end-to-end communication with 6G. We have a consortium in which, besides some telecommunication companies, we have some partners from the application domain, in particular from the industrial side here. And we look into system aspects for end-to-end communication with 6G, from the use cases, the requirements on how to improve and provide technology enablers that increase the determinism and dependability of the system for critical kind of applications. And we also work on a validation framework. Some of the time-critical applications that we look into, we see that the number of time-critical applications is increasing, not only in industrial automations, but there are other fields. Extended reality is another example in the more consumer market. Smart grid applications, there's a large number that could be listed here, and all they have in common that they typically have some kind of require some guaranteed latency bound, and that high availability is important because it's critical kind of services. Some of the use cases that we explicitly investigate in our Deterministic 6G project is occupational exoskeletons, extended reality, flexible production, and smart farming. And these applications can be all described in the context that we are on the move towards the cyber-physical world, where we separate the physical machines and assets from their logic that is then moved into the digital world, often via a digital twin. And that means that a lot of the logic for controlling the physical world is basically, it becomes programmable from the digital side, which means we offload computing and logic from this physical world to an edge cloud. And this can be, for example, for the purpose of spatial compute and extended reality, or when we have control applications, making control applications more machine learning friendly, or enabling better collaborations between a larger number of assets. But it can also be strongly motivated by device simplicity. If we have an XR class or a mobile robot, then by putting away the compute from this platform, we can reduce the power consumptions, the footprint in space and weight, and the complexity of a physical device by moving the compute into the edge cloud. So some of the requirements for these time-critical applications is that they need time awareness, since we're time-critical. So time synchronization is often something that is required in this context. And these applications are end-to-end, often realized with some specific kind of networking technologies like time-sensitive networking if we are in the LAN segment, or deterministic networking in the IP world for providing this end-to-end connectivity. And when we want to support this with 6G, then we want to work on dependable time-critical communications. And what this means, dependable means that the application can rely on that the network supports whatever is needed from the application. And a more technical way of describing this, we must be able from the network to ascertain that we can deliver the service performance that we have agreed on at the service request. And this comprises several steps. It means that we need quite clarity on what are the requirements and what is the agreement on the service performance that needs to be delivered. We also need capability for monitoring and predicting the service performance that is actually provided from the network. Then we need automated service assurance, and we need the possibility to provide feedback back to the application domain on the service performance that can be delivered. And this enables then for more application communication co-design choices. What is important is to define really a good and rich service interface where both the traffic characteristic of the applications are defined, but also the latency bounds and the reliability, but also the robustness that the application has towards network variations. A second very important part in this is that we must have good monitoring capabilities for being aware of what is the service that we are actually delivering over the network. And from that, we want also to be able to predict what is the performance that we can deliver in the future. And that means that what we look into in deterministic 6G is that we do this service prediction based on collecting observations from the network performance that is being delivered and applying machine learning for performance prediction. And for this, we need then, of course, a framework where we can have this data collection, a data pipeline for connecting this and applying machine learning reasoning. Then, based on these applications, we need to get a description from the applications on what are the priorities in service delivery. So with an intent interface, providing rules to the network that the network can do service assurance and optimizations on the service delivery based on what is valuable for the application. And what is important is that we can close the loop and provide feedback back to the applications on the service that has been delivered, but also maybe this can be used in case that we, from our prediction, see that we come into the situations that the required performance cannot be provided to give opportunity for the application to take countermeasures. And in general, I think in these interactions between the network and the application domain, we see that there's a lot of possibility for enabling a co-design on how the application makes use of the network, and where applications can also be defined in a network aware way, so that optimizations of the resources in the network can be considered in the service delivery. So, as I said, a lot of this communications happens in the end-to-end over some, for example, TSN network or DetNet network. And it is important to be possible for the 6G system to interact with these external networks. So the integrations there. There's also work ongoing on some application middleware for configuration of deterministic communication end-to-end, for example, in OPC UA. And what we want to have is that we can optimize this integration of 6G with these internal domains. And so there we explore several ways on how we can have optimization capabilities between, for example, TSN and DetNet with 6G. And there we have done quite a bit of work on TSN support already and DetNet support in 5G, where we see where can we take next steps of improving this kind of interaction. And with this, I'm at the end of this presentation, and I can say that we have finalized a couple of reports which describe a lot more details on some of the aspects that I have touched here now, and you can find them on our website. And with that, I'm at the end of this presentation.